So today, did not think this would be today, but apparently we're supposed to have fun today according to my schedule. Mainly because, so I'm going to use this as an opportunity to try to continue with learning teaching you dictionaries. So a lot of the information we're going to be storing will be stored in dictionaries. We're going to be using the counting functionality for dictionaries for today. But a lot of what we're going to be doing today, if you scroll down, you'll notice that the videos are different. They're not me talking, and they're not related at all to the textbook. You see, I'm a very lazy person at heart. Math, as you see, and is hard and takes a lot of effort. And answering difficult math questions is hard and takes a lot of effort. So I don't do that. I don't do that because that you probably have. They're pretty good. So we're going to learn about something called the Monty Hall problem, and we're going to learn more specifically, we're going to learn about something called the Monte Carlo method, or performing Monte Carlo approximations. This is something you would typically get hit with in a higher level math class, but don't let that scare you, because the entire point of it is to cheat at doing higher level math. Okay? So let's talk about where the name of this comes from. Okay? And we're going to do that by going to maps.google.com. And for once, I don't have to worry about accidentally doxing my address because I'm not logged in here. Okay? So we are going to go and we are going to look up what the heck is Monte Carlo, because that is a place. Monte Carlo is a small area in the micronation of Monaco. Micronations are this weird phenomena in Europe. There's a couple of micronations. You can see, like over here, Vatican City is probably the most famous ones, but as well as Luxembourg and Liechtenstein. Luxembourg is actually quite much larger than Monaco. But also, like, you've got nations like Andorra, which is this little thing that's right between France and Spain. You know, and that it's got a very interesting system of government. Let's see, like, oh gosh, Andorra, yeah, and yes, people, like, yeah, this is such an interesting thing. Government is unitarily constitutional co-principality. Yes, they have co-princes, one of which is Emmanuel Macron, because it is the the president of France is always a co-prince of Andorra. The European history is wild, okay? It is really wild. So anyway, Monaco is not Nice, that's a completely different place, but let's go back to Monte Carlo. Monte Carlo is probably most famous for the Monte Carlo Casino, which is this is specifically what we're naming this after, okay? Monte Carlo Casino. Very famous casino. You can see it looks very posh, very nice looking, okay? Very famous, okay? And the point about casinos is that, of course, as you well know, they're meant for gambling. And this is actually going to be the focus of about a week's worth of lecture. Gambling. Yes, you didn't realize that this would be the class. But no, it's more about why gambling is a bad idea. Just off the top of the head, anybody know what the game that has the best odds at a casino are? Yeah, the least house advantage, yes. Craps does not have the best advantage for, the least house advantage, yes. Baccarat? I'm not sure about Baccarat, but it's very close to Baccarat. Not slot machines, but it is blackjack. Blackjack has the house advantage. Sorry, has the smallest house advantage just by naturally playing the game. And if you card count, the advantage is actually in favor of the player. Card counting is not illegal. Gambling is not. By the way, gambling is not a surefire way to win money. It's actually a terrible way to try to win money. That's why casinos stay in business, because they make money off of people who, are. Like, the only way to get money at a casino is by working at it. Exactly. He understands that the only way to get money at a casino is to work at the casino or to own it. There you go. That is the only surefire way you have. That is the only surefire plan to make money at a casino. Anyway, but suppose you. But I mean, like, so games in general have these certain statistics involved with them. They have these probability of winning and losing. But suppose you walk into a casino, and you're watching a game and you don't really understand the rules. How do you know what your odds are? Your statistical odds are for winning or losing. And this is where the Monte Carlo method comes in, which is just simply says, long story short, you're going to watch the outcomes of all the games. And you're going to be basically you're going to count the number of wins versus the number of losses. And if you watch enough of those, that will approximate the actual statistics, right? Right? Suppose that you had a weighted dice, right? A weighted 6-sided dice, and you rolled it, and one side of that dice was going to come up more often than the other, right? Maybe just a bit more often. How do you figure out what side that is? You roll it a bunch of times and count the number of times each number occurs, right? So you'd be able to figure out which side is going to come up more often, okay? And you could have to do it a lot of times to be able to figure that out, okay? And of course, if everything kind of evens out, they don't have to be exactly equal, right? If you flip 10 coins, you flip 10 coins, it's not going to end up with 5 heads and 5 tails. In fact, that's not a very high chance. In fact, let's go ahead and start that out right now. Actual question on an exam. Actual question in an exam that I've given on over this material. Okay, on exam 2. Suppose I challenge you to a game of chance. Okay, and the rules for the game of chance are as follows: you flip 5 coins. If 5 of them end up on heads and 5 of them ends up on tail, you win. You win $1. And if they don't end up, and if otherwise, I gain the $1, right? Okay? So it's $1 up for grabs. If you flip 10 coins, get 5 heads, 5 tails, you win. Sorry, 5 heads, 5 tails, you win. Otherwise, I win. Then the question is, what are the true odds of the game? Right? I mean, the lie is that I would tell you that you have an equal chance of winning or losing because because we're flipping 5 coins, 5 heads, 5 tails, that's half of the coins going to heads, so obviously that's a 50% chance of winning. This, of course, is not the only outcome. But you don't know statistics. You haven't taken a statistics course, so you are vulnerable to these types of scams. Ostensibly, you probably actually are suspicious that your professor is trying to bet with you in the first place. So let's go ahead and just open up I think I have idle on this machine. I should. It's no problem with any. Right? We have Python 3.13, and then we have idle. Yeah. This is perfect. Perfect. I mean, okay, and yep, here it has the configuration from last time. So we're going to just simply program this out. So the key library we use for this, and again, this is an actual question I asked on my exams. Okay, the key to figuring out this is that we have to use the random library. Okay. So how do we figure out the true odds for this game? Well, we play the game. We have the computer play the game a lot of times. And when I say a lot of times, I mean more than 10,000 times, right? But we can automate that, right? We could make a game function, right? Def game, just thinking high level here, right? Def game, and we're going to return, we might return true or false. We'll replace this later when we want to collect better odds. But let's assume that true means we win the game, false means we lose the game. And then we could just simply do something like this. Wins is equal to 0. Trials, which I'm going to put in all caps because that's what we do for like a constant, a variable that we're not going to change. That's kind of denotes to other programmers, hey, this is something I'm not going to change. That's why you might see people write pi, their variable for pi as pi is equal to 3.14159, but use capital letters. Capital letters indicates that this is something we don't want to change too much. So might do it 10,000 times, and what I'll do is I'll say for in range trials. What I'm going to do is I will do, and this is what all I'd expect on an exam. Not all I expect, but I just basically expect checking if we win or lose on the exam, right? So for I in range, so if game, or actually let's go ahead and split this out because you could put it in the if statement, but again, readability is always great. We'll run a game and we'll get the result. If result equals true, if we won the game, wins +1. There is no else. Simply, we can figure out, right, because we're just counting the number of times we win, and the number of times we lose can just simply be figured out by going trials minus wins, right? Okay, we could count the number of losses, but that. Also, we can just simply get rid of this equals true because true result is going to be true or false, so it will be either if true or if false, right? So we can just shorten this. So we run the game. If the result is this, then we win. And then we can just simply print out for the actual odds, print is equal to wins divided by trials, right? And that will give us this will give us a number between 0 and 1, right? This will give us our percentage chance of winning, okay? So now let's go ahead and program the game. The game relies off of flipping 10 coins, right? So in order to figure out how to flip a coin, we are going to import random, and we're going to make a function to flip a coin. I know that seems silly, but it's useful. And there's this nice function for that, and I'm going to make this abstract. I'm going to use more lines than I need to make it abstract because that way you can see it goes to dice as well, even dice with special sides or picking cards. But let's say, coins and dice have sides, and so we can make a list of what those sides are, right? The sides are heads, I'm going to use H, and tails. Now in other programming languages, you have to do annoying things because random number generators only generate random numbers, pretty much. Like you can get to generate a random float or random number. Python's awesome because it does a lot of things that you often have to program yourself, such as choosing something from a selection. So we could do, I think it's called random dot, and I believe that is, random dot, and then I think I have to give it a second to choice. Yep, random dot choice, sides. It chooses a random single element from a non-empty sequence. In other words, this non-empty sequence. So this is a sequence and it's not empty, right? It has stuff in it. That's what non-empty means. So random dot choice sides is so we'll just go ahead and return that. So this will give us a heads or tail, right? We can test that by, I'm just going to copy this into here. Okay, yes, import random. And then I can copy this into here. And then I can call flip. Okay, and it tells me I have an error, random.choice sides. Let's go ahead and instead run this program. Run, and yes, it's giving me 1.0, but now flip is loaded up, so I can call flip again. And it'll give me heads, heads again. You think it would be, and there you go, tails. So we're getting heads and tails. It's going to randomly choose it, and randomness doesn't necessarily, so here's the important thing about randomness. Randomness means statistically random, and that statistical randomness is only really true after a lot of runs, right? So anyway, so for instance, like, let's go ahead and just simply run this. I'm going to hijack this. This is not something you want to save. But if I simply was to just simply say if flip equals H. Actually, we're just going to short circuit this. Return flip is equal to H. And this will return true if and only if flip is equal to H. And I'm going to immediately delete this, but I'm just trying to show you that basically it wasn't exactly half of the coins. It was close to half of the 10,000 coins, but it was 0.497. So not always 50-50. Yes?
I can't get the flip function to work. It was working fine for you, but I couldn't.
Did you accidentally do what I did, which was sides and side? I accidentally put a side over here. I accidentally had this as opposed to sides.
No, I don't believe.
Check your indentation and stuff. Okay, def game. So now what we need to do is basically, so the game, if you remember, was you flip 10 coins, you get half heads, half tails, right? So for a purpose, now we could just simply do let's go ahead and just simply count them, okay? We're going to count the number of times that we get these numbers, okay? Okay, we're going to just simply do num heads is equal to 0, num tails is equal to 0, and we got to flip 10 coins. 4, range, 10, if we're gonna do side is equal to flip if side equals h. And yes, I'm over engineering this in terms of length. I could make these a lot simpler, but again, I value readability. Num heads is equal to plus equals 1. Else, since there's only two sides, I can easily just simply say else. Num tails plus equals 1. And yeah, I could just simply keep track of the number of heads and number of tails. I could keep track like this. I could also just keep track of the number of heads, right? But now we're going to return num heads equals num tails. In other words, if they're both equal to 5. That's the only way they can both, if they're equal to each other, right? And now if we run this, now we both know because I presented this as a scam, that it's going to be a scam. But I don't think you realize quite how much of a scam it is. You have only a quarter of a chance of winning that bet. If I ask you to bet 5 heads and 5 tails, right? 5 heads versus 5 tails. What are the chances that half of them land on heads and half of them heads on tails? It's a quarter of a chance. And that's because there's a lot of other results that happen. There's 6 heads, 4 tails, 6 heads. In fact, let's go ahead and use a dictionary. I'm going to create a dictionary called count. Now, everything I wrote here, this is basically this is what I'd be looking for on the exam. What I'm about to do is extra practice with dictionaries. Counts is equal to dictionary. Okay? And what we'll do is we will say, since we have all these results, let's see. We'll set it up, we'll do the setup here. For in range, for I in range, okay, 0 to 11, right? Yeah, I think it would be 0 to 11. Counts of I is equal to 0. What are we doing here? Basically, there's 11 different possibilities when we flip 10 coins, right? It's going to be heads or tails, right? So it should be 11 different possibilities. And one of that 11th possibility is, what if none of them end up on heads, right? That's why we start at 0. What if we flip 10 coins and none of them ends up on heads? Then what if 1 coin ends up on head? 2 coins, 3 coins, 4 coins, 5 coins, 6 coins, 7 coins. Make sense to everybody? So this is just basically the number. So the key here is the number of heads we got, okay? And the value is the number of times we got that result. So now, whenever we do this, we're going to flip our 10 coins. What I'm going to do right now is I'm going to say count of num heads plus equals 1. I don't have to check if it's already in the dictionary or not, because we know it's in the dictionary, because I initialized it to say it would be. And basically I'm saying, hey, we are just simply, and you could easily do this with a size 11 list, where basically you say index 0 is the number of times you saw no heads. Index 1 is the number of times you saw one head, right? Dictionary, though, this again, getting practices here, I just established it and said, hey, we're getting all these things, start at 0. So we have the count there, and then we can print out our win rate. And then what we're going to do is we're going to go for num heads in, sorry, here we go, for the number of heads in count. Did I say count? Counts. Counts, sorry about that. Counts. I normally do it as count, but I guess I did it as counts this time. For the number of head in counts, print num heads and then counts num heads. In other words, the number of heads that I got plus the number of, and then print out the number of times I saw that result. And we'll see that we get this bell curve, actually. Let's go ahead and actually divide this number by the number of trials to get a percentage. That'll be a bit easier to read, I think. Okay, run module. So now we can see, right, it's very, very rare to get no heads or all heads. Very, very rare. Very, very, very rare. It happened like 6 times. Whereas, again, we get close to 25% chance of getting the 5 heads and 5 tails. It's very, very, and between getting 5 heads and 5 tails and 4 heads and 6 tails and 6 tails and 4 heads, that's about 50%. That's like 65% right there, which is kind of, that feels about right. But we get a bell curve. The point is though, that you don't know statistics, and that's fine, because we can cheat at knowing statistics. In fact, knowing statistics will not save you, ever, because humans are not good at paradoxes. So we're going to use Monte Carlo approximations to really introduce a different kind of Monte, okay, which is possibly one of the most famous mathematical paradoxes we've seen, or mathematical problems we've seen. It's a paradox because it feels wrong. And what we do to find it is you're going to go to Runestone. You can either click on Module 9, Monte Carlo approximation. Oh, hold on, I need to edit that. I forgot to edit that for today. So I'm going to go ahead and hit this. We are going to hit the link options, and I'm going to go ahead and modify this so it says Spring 2025 Rosen. Done. And then we are going to do, Spring 2025 Rosen. Hit save. So now that link is good, but in case you wanted to go find it yourself, go to this web page. Right? So now, sorry, you can go to Module 9 now. You should be able to just scroll down and click on this lab, this exercise. But otherwise, you can scroll all the way down here, right, to our projects. And we go to the one after exploring common words and setting, and Monte Carlo simulation. I did Monte Carlos all the time in graduate school. They're very cool. One of them we're going to do it completely out of order, okay? Completely out of order today. So we're going to go down to there's 3 sub-problems. We're going to go to the third one. The Monty Hall Challenge. Video's unavailable, unfortunately, but that's fine because we're not going to watch that video anyway. There was a game show in the 70s called Let's Make a Deal, okay? And the idea here is that basically, as part of Let's Make a Deal, there is this choice to be made at the end of the game. Monty Hall problem. There's a choice to be made. And we abstract the problem as to having 3 doors, okay? 3 doors. Behind 2 of those doors is a goat, and behind one of those doors is a fancy new car. So now for the sake of argument here, because my wife is the person who she is, I have to, say, for the sake of this problem, we value the car more than we value the goat. She's the type of person who would want the goat. So, so anyway, we've got some valuable prize. And then we've got 2 goats, which are our booby prize, as they say, I believe. They are not very good prizes. So the idea here is that it works specifically like this. It's very important that the problem formulation is specifically like this. Monty, the host of the game, will say, choose one of the 3 doors. Okay? Choose one of the 3 doors. So let's say you choose door number 1 or 2. Let's say I choose door number 1. In fact, for the sake of this problem and ease of programming, we're always going to choose door number 1. Okay? Monty, the game host, will then open one of the 2 remaining doors to reveal a goat, which he can do because he knows where the goats are, and there's 2 goats. So if you chose a goat, then there's always going to be a goat to open. So he's going to open a door and reveal a goat. And then he asks you a crucial question. Do you switch or do you stay? Do you feel good about your initial guess, or do you want to switch? Switch or stay? You want to switch. So the question we ask is, what are the odds if you decide to switch versus if you decide to stay? Yes?
If you stay, it's 1/3. If you switch, it's 1/2.
You switch, it's 1/2. Any other takers?
I'm pretty sure the statistics is like, stay with your initial guess, you have a 1 chance of winning the prize, but if you switch your guess, you actually get a 2 in 3 chance of winning the prize.
Yeah. Then you really have to be exposed to this problem. Have you seen this one before?
Yes.
Yeah, so you really have to be exposed to this problem to know what the correct odds are, which is that it feels like if you switch, you've got a 50-50 shot. Now there's 2 doors, 50-50 shot, right? The odds are actually 2/3. If you switch, you have a 2/3 chance of winning. Because of that first statement you said, which is that if you stayed, you only had a 1/3 chance of winning because you had only a 1/3 chance of getting it right in the first place, right? But if you switch, you're switching to the other possibility. And the possibilities always have to add up to 1. Always. Now, again, he's always going to reveal the goat and not the door. If this feels odd to you, let me let me give you the Professor Rosen explanation, which nobody else gives. Imagine instead, if you will, rather than having 3 doors, we have 1 million doors, and we have 999,999 goats. It's a lot of poop, let me tell you. Okay, so now let's go ahead and say we choose our initial door, say door number 1. Okay, now Monty reveals 999,998 goats. He opens all but your door that you picked and some other random door. And so now you've revealed 999,998 goats. Do you switch or do you stay? Right? It feels, and suddenly that kind of brings it into line, because your original guess was 1 in a million. Now, everybody knows that 1 in a million chances in fantasy happen 9 times out of 10, but this is not fantasy, this is math, and so we have to go with the hard statistics. So so if we switch, we kind of have really increased our odds here. Now, yes?
Wait, so after the door,
Yes.
1 out of a million, then I don't know, opens,
Monty Hall is the guy. Monte Carlo is the technique we're using. No worries. It's confusing.
then they open all but 2 doors.
They reveal all but 2 doors. The one you chose and the one that the car is behind.
Oh, that makes sense.
Okay. Ostensibly, okay. Now if you feel like that is confusing, okay, this is why I say why knowing statistics may not save you, okay? Right? This was asked to Marilyn Vos Savant. Marilyn Vos Savant had an extremely high IQ. IQ is a weird measurement for intelligence, but generally speaking, if you've got a really high IQ, you probably have some amount of very good reasoning skills for a number of things. Anyway, she ran a column in Parade magazine, and this was the question asked in 1990. And she correctly responded saying, hey, it's a 2/3 probability, okay, of winning. Many readers of Vasavant's column refused to believe that switching was beneficial and rejected her explanation. After the problem appeared in Parade, approximately 10,000 readers, including nearly 1,000 with PhDs, wrote to the magazine, most of them calling Savant wrong. Even when given explanations, simulations, and formal mathematical proofs, many people did not accept the switching was the best strategy. Paul Erdos, one of the most prolific mathematicians of the time. This is Paul Erdos. Okay. He had trouble accepting it until he was shown a computer simulation, which is what we're going to do today. Okay. The problem is a paradox of the Veridis. I don't know how to pronounce that word, but the solution is so counterintuitive, it seems absurd. Okay. And this has been studied well beforehand, but Paul Erdos, when we say he was prolific, we mean that he was extremely prolific. 1,500 mathematical papers during his lifetime. In fact, those of you who are attached to the acting community, you probably know about the Bacon number, right? Anybody know the Bacon number? The Bacon number is, if you've acted, that's the number of degrees that separate you from Kevin Bacon. So if you've got a Bacon number of 1, you've acted with Kevin Bacon. If you've got a Bacon number of 0, you are Kevin Bacon. If you've got a Bacon number of 2, you've acted with somebody who's acted with Kevin Bacon, which would be so you've acted with somebody with a Bacon number of 1. If you've got a Bacon number of 3, you've acted with somebody with a Bacon number of 2. Paul Erdos is the mathematical equivalent of a Bacon number. If you've got an Erdos number of 1, you published with Paul Erdos. He's dead, so that's a bit hard to do at the moment unless you're really good at necromancy and divination. So, with regards, if I managed to somehow acquire an Erdos number of 5 because my advisor had an Erdos number of 4, which he did not know. But apparently there's ways to track that down. So, and if you've got both a Bacon and an Erdos number, then your Bacon Erdos number is is the higher of the two. Yes.
Have you heard of the theory that you know every other person in the world through
6 steps. We'll be covering that in a few weeks in 2168. That was discovered by Stanley Milgram of the Milgram shock experiments. Or not discovered, but demonstrated through a much less well known. But the idea here is that you can route in networks like human connections by making very large leaps followed by very small leaps. So Paul Erdos, anyway. So if you are confused by this, by the mathematics of this, and looking at the Bayesian statistics, right, using Bayes' theorem to solve these statistics, don't worry, you're in good company, right? I didn't get it until it was explained to me. It seemed counterintuitive. I've done this so much, I don't see how it could be anything but the solution, right? Like, very simple solution, right? Let's assume you choose, here's your 3 possibilities, because the car is all that matters, right? The position of the car, that's already all that matters. Possibility 1, car's all the way over here, we reveal the middle door to reveal a goat. You initially chose a goat. If you switch, you win. Here's a goat. Car's over here, we reveal the other goat over here. You switch and win. Finally, third possibility, Monte Carlo is going to reveal a goat being behind one of those doors, but it doesn't matter because if you stay, you win. If you switch, you lose. So in 2 of these possibilities is switch and winning. 1 of these is stay and winning. Make sense? It's the easiest way to kind of explain that. Okay, so we can very easily do a simulation of this, through Runestone. Through Python, and we're going to just put this into Runestone. Okay, so I'll go ahead and walk you through this. This one is pretty fun, I think. Import random. So again, Monte Carlo problems, we're always going to need to import them. What does Monte Carlo mean now? So now that we're doing it again. Monte Carlo means if I don't know what the statistics of something are, I am just of some kind of game. We're going to abstract this out to a game. If I am playing a game and I don't know what the statistics for winning and losing are, I'm just going to have the computer pretend it's playing the game. Okay? And then I can count the number of times it wins versus the number of times it loses. If I do this, if I have the computer play the game enough times, I will know what the statistics are. Or I will get my estimate will get closer and closer the more times I play it. Yes. That was not a question. That was stretching. Okay. So def, we will go ahead and I will do a setup function here, which will set up our goats. Return none, which just means I'm not doing anything. Then I'm going to set up my game. Same kind of deal here. Return true or false to say whether I win or lose. So set up game, right? And now what we're going to do is very straightforward. This is going to look very, 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 very similar to what we just did. Wins equals 0. Trials equals 10,000 trials for in range. Are you getting the hint that this bottom portion is possibly identical no matter what problem you're doing? It's not actually identical all the time, but it gets darn close. If result, I'll do it exactly the same though. Result is equal to game. Run the game, store the result. If result equals true, which again, we don't need that. We can just simply say if result, wins plus equals 1. Print wins divided by trials. So we're just simply going to we're just going to count the number of times we win. This is almost always the same for everything, right? I think one of the only few times this will be different was like for a practice problem in the practice exam I'll give out is a Monopoly problem where I ask the number of times you get, how many doubles did you roll in a turn? Did you roll 0, 1 double, 2 doubles, or 3 doubles? And that's just keeping track in a much smaller kind of, in a very small amount of variables, and it's very easy to keep track of. But for the most part, it looks like this structure for running a bunch of trials of this. Okay, setup. So to set up, we have our goats and we have our doors. So we're gonna. Okay, so it's going to take 3 steps. First, I'm going to teach you a new random method. So we're learning 2 random methods today that are very valuable. The first is random.choice, to randomly choose something out of it. This one I like a whole lot. This is called random, and this is to set up problems like this one. So we have a, here's our doors, right? Here's my doors. And we have a goat, G for goat. And remember, we consider the goat undesirable. Personally, I wouldn't mind a pet goat myself, but goat, and car. Now, obviously, we need to kind of change this around. So we could like randomly choose the number 1, 2, 3 and write some if-else statements to figure out which one we wanted to put, where we wanted to put the car. But that's boring when we can make Python do the work for us. Random.shuffle. Not shiffle, shuffle. Shuffle, doors. Random.shuffle's very, very cool. And it does exactly what you'd expect it to do. I'm just going to go ahead and I'm going to run it and print it a few times so you can see how it works. But I think you already know exactly how it works because it's in the name. Right? It moves around where the car is. I mean, it moves around the cars and the goats, right? If I call them goat 1 and goat 2 to differentiate them, we call them goat 1 and goat. We went into overwrite mode. Don't do that. Okay. Here we go. Stupid overwrite mode. Here we go. So now we can see the goats swap around all over the place. We're probably making them very dizzy by making them move back and forth between these doors. Okay, so there we go. We've got our goats and the car set up. Panopta doing good? Yeah, I think it's doing good. Okay, next we've got our, now we just got to play the game. Right? But we've done the first part, which is getting the setup, right? Doors, is equal to setup, right? I could have done this inside of game. I just chose to do that as a separate thing so I could easily test it, right? Easy to test that. So again, statistically speaking, there is no difference between which door we choose, right? So it's just simply easiest to choose the same door all the time, right? There is no difference. There is no way for us to know the difference while playing the game if we are playing, which door we should choose. So just simply choosing the first door just makes things simpler for us. So choice is equal to doors 0, right? And honestly, it leads to a very simple solution. If choice, we don't really even need to know this, right? If choice equals a goat, then Monty reveals then we lose because, if our choice is a goat, actually, let's not lose. If our choice is a goat, we win. Return true. Else, and I'll just turn this into a return false, which again, I will shorten in just a sec. I'll show you we can shorten that greatly. So if we choose a goat to begin with, we win. Why? Because Monty will reveal the other goat, meaning the only other thing is a car. So if we switch, we win. Make sense? Meanwhile, if we choose a car, and we decide to switch, we're going to switch away from that car, so we lose. Make sense? Yes. We can actually do that very easily. Strategy. That was going to be the next part, so give me a second. So we're assuming we're always switching here, okay? Save and run. And we see over here 0.67 chance of winning if we switch. Now to answer your question, can we define whether we switch or stay, what our strategy is? I can define this. I'm going to do something, I'm going to take the opportunity to teach you something weird with an argument that you can do here. You may have seen this before, but this is pretty cool. I just simply said switch is equal to true. Okay. And that just runs. So what I've just added here is something called a default argument. What I've done here is that I've said this will take in an argument called switch. And that will tell me whether I want to switch or not. So if I put over here true, because I want to switch, great, same possibility, 6, 7. If I don't want to switch and I put in false instead, it says I win 0% of the time. Right, because else, okay, yep, sorry, give me a second. Else if choice equals car and switch false, turn true, right? Because if we chose a car and we're not switching, then we win. And that gives us a 0.33 chance of winning, right? So there are choices. If we end up with if we have a goat and we're switching, great. If we have a car and we're not switching, that's great too. Okay? And then finally, the else here is that, well, if you didn't win, then there's only one possibility. There is no tying in this game. You lose. Okay? So, what did this say? There's 3 possibilities for arguments. We can say we are switching. We can say we are not switching. Or we can say we're doing the default thing. So when I have a argument, when I don't have a default argument like this, right? If I run this, it's going to tell me, hey, it's missing a required argument. Note that word that you've been reading this entire time, every time you've had an error and you forgot about putting in an argument, it said required argument. That implies there's arguments that are not required, and that is true. There's tons. Python is full of arguments that are not required. And the way we do those are default arguments, where we say, hey, if you don't give me this argument, it says, hey, you can give me this argument. It's not required. If you don't give it to me, it's going to have a default value. It's going to be true. So by default, this is going to be true. If you pass in true, great. You agree with me. And if you pass in false, okay, cool. It's going to be false now. So another thing we can do, by the way, over here is let's go ahead and just simplify this just a tad. We can go and say, if the choice is a goat and switch, so if we choose a goat and we switch, and we can rewrite this one to if goat and not switch, if car and not switch. And rewriting that becomes really, really nice. Okay. I'm going to go ahead and share this code with everybody so you can reload it. Okay? So you can reload it and you can get to it. Because now I got to do my the part of my lecture that ends with everybody going ooh ah, which is why I like this particular lecture. On Thursday, by the way, we will continue with doing this. Only we will do some other games, such as what are the odds of flipping over cards, in the correct order. So things that do look like the mathematics should line up at a first glance. So we're going to just play a lot of scam games, or games where basically that somebody at a bar might be trying to scam you out of some money, right? If it seems too good to be true, right, don't. Gambling's a bad idea, especially with strangers, because you never know if the person you're playing with is really good at shuffling cards. And also keeping cards that he should not up his literal sleeve. All right. So we're going to go back quite a number of weeks at this point to this, approximating pi. Everybody remember this, the Madhava-Leibniz function from the beginning of semester, where we started out for loops, which was calculating this value of pi over 4. Remember that? We were calculating pi over 4. So that was 1 over 1 minus a third plus a fifth minus a seventh plus a ninth, and so on and so forth. And if we kept doing that and doing that and doing that, that would approximate the value of pi over 4, right? So we could multiply this entire thing by 4 and we'd get pi. We did this, I think, during our 5th lecture, okay, as kind of an introduction to doing for loops. And we started out by doing 1 plus 2 plus 3 plus 4 plus 5. Then we made it 1 plus 3 plus 5 plus 7. And then we made it 1 over 1 plus 1 over 3 plus 1 over 5 plus 1 over 7. And then we learned we can just simply swap them back and forth. So it was built. So we learned how to build that up. Okay. The Monte Carlo simulation is a lot more of an intuitive, fun way, I think. I don't find it intuitive, personally. I find it pretty unintuitive, but hey, teach their own. Microsoft Paint. Yeah, no, I don't need this. We're going to instead take advantage of the fact that we've got this. We're going to draw a square here. And we're going to draw, actually what we're going to do is we're going to draw this. This, of course, is, right, I say of course, but what this is, what we are drawing here is the unit circle. Okay. Okay. What do I mean by the unit circle? Right? The unit circle has a radius. And the radius is 1. That's what it means to be a unit circle, right? Everybody's familiar with this from trigonometry, right? The unit circle. Don't worry, we're not getting into weird cosines and angles and stuff like that, okay? This is a fair, I'm just kind of showing you what we've got here. And around this circle, I'm going to do my best to do this. And then can I? Yes, I can move this. I can build it, and then I can move it over. Okay, great. Oh, that was so much easier than I thought it would be. Okay. And so now around this circle, I've built a square. We can logically know a bunch of things about this square, right? We know, so first off, this is a square that is on top of the unit circle, okay? So this is the center of that square as well, right? Makes sense? The center of the circle is the center of the square, and the radius of the circle goes all the way up to the side of the square, right? So in other words, we know that the side of a circle of this is 2. Make sense? Because the radius of this is 1, so the diameter of the entire circle is 2, right? Radius of the circle is 1, diameter is 2. It goes, the square is as big as the circle, so it goes end to end. Make sense? So what I built here is not a knockoff Deathly Hallows, but instead a dartboard, okay? The idea here is that I've got a magic dartboard, and we're going to throw darts at it, okay? This is the entirety of the simulation, right? So the circle, right? For those of you who need a visual reminder, right? Dartboard, right? Here's a dartboard. It's a circle inside a square. But it's a magic one with a force field so that all the darts either land inside the circle or they land inside the square. In fact, everything's going to land inside the square, right? All the darts you throw are going to land inside the square. It's not going to go off into the distance somewhere. It's either going to be inside the square, and if it's inside the square, it can be either inside the circle or outside the circle. So there's no if about it being outside the circle, okay? So what we're going to do here is we are going to look at the ratio of throwing the number of darts on the board versus divided by the total number of darts. What is the ratio we get if we throw the number of darts divided by the number of darts on the board? Okay. So again, this dartboard is in the middle of a square that's 2 by 2. Like it says, magical force field that ensures all the darts land on either the dartboard or the 2 by square. And what we're going to do is we're going to use turtle and random. And we're going to simulate the turtle landing in some position. We're going to, because we're now talking about turtles, right? This is going to be 0, 0 over here, right? This is going to be 0, 0. And then this over here, that means that this needs to be -1, -1 in the coordinate plane, and this corner is going to be 1, 1, right? This is just the coordinate plane. Have I scared anybody yet? Right? This is not too, everybody's following so far, right? Okay. So what we're going to do is that we're going to randomly generate a point on this in this limited square and tell this turtle to go there and stamp his belly there, so that he can just simply make an imprint for visual. And then if he lands inside the circle, that's a hit. And if it's outside the circle, it's a miss. We'll go into the formula for that in a bit. Okay, but here's the part where I lose people. Since the area of, so first off, what's the area of the circle? So the area, so the rate, what is, sorry, let's just even make this simpler. The formula for the area of the circle, as we've learned, is pi r squared, right? That's the formula for the circle. Okay? What is the formula for a square's area? For a square's area. Not a trick question. Not a trick question. How do I get the area of a square? Not the perimeter, but the area. Yep, the square of the side. So let's call the side length S and square it. Okay? So we can compare, so we can say, hey, if we put this as a fraction, this is the amount of space that the circle takes up inside the total area of the square. Make sense? Everybody following so far, right? Everybody got that so far? So if we take this is the amount of space the square is that the circle is taking up out of the total amount of space available. So now that we actually happen, because I've defined this as a unit circle, we know the numbers. First off, r squared, what is r? This is a unit circle. Radius is 1. So we can just simply remove that because 1 squared is 1, right? Now, the side of this, because the diameter is 2, right? And that's going to be the same length of the side of a circle. Oh, sorry, the side of a square. S is 2. 2 squared is 4. Make sense? So the area of this square is 4. So the ratio, so the amount of space, the ratio of the amount of space that the circle takes up is pi. Sorry, the amount of space, the ratio of the space of the circle to the square is pi to 4. So in other words, pi over 4. And the idea here is that if we throw our turtle enough times, then the ratio for what the turtle gets of hits to misses, because hits is the number of areas that land inside the circle over the total number of, total amount of area there is, hits to misses, that's going to approximate phi over 4. Okay. So by doing this, we're going to be able to get our answer. So with that, I have plenty of time to program this out, and it's going to look very, very nice. So what we're going to do over here is import turtle. Okay, and the first thing I need to do is set the world's coordinates. I believe I have to do, so turtle world coordinates. And now this is something that you didn't have to do in Turtle, and you'll never have to do in Turtle yourself, but it is what was done in your IRMA program, set world coordinates, where what we do is that we say, hey, typically like the turtle space is like a 100 by 100 kind of grid. Here I want the turtle's square that he moves around in to be shrunken. So we're going to define we're going to define the dimensions of the square. So here it says LLX, LLY, URX, URY, which are very, if you don't already know what we're looking at, is very uninformative. But what it's saying is lower left X, lower left Y, upper right X, upper right Y. What it's saying is, what are the corners of the box the turtle's going to be in? And I defined that already. -1, -1, +1, +1, right? So what we're going to, and allow me to demonstrate, right? If I tell, I'm going to go ahead and make Bob is equal to turtle.turtle. Okay? And then I'm going to tell Bob dot go to 1, 1, right? He barely moves at all, right? And we'll go ahead and say turtle dot shape turtle. Is it shape or set shape? Yes, shape. So yeah, he barely moved at all, right? But now if I say something like this, turtle dot set world. Let me just check. Is it? Yeah, it's all lowercase. Set world coordinates. -1, -1 for the lower left corner, and 1, 1 is the upper left corner. And then you can see, Bob. It should be bob.shape. You can see that the turtle, right, when we tell him to go to 1, 1, he goes all the way here, right? So we've said this is now, so we can see that we've actively got our square that we're working in, okay? We are going to go ahead and now make our function. Import random. And what we're going to do is we are going to do a function called throw to make the turtle. And the way it's going to work is that it will throw the turtle at a random location here. Sorry, Bob. And what we're going to basically say, if it lands inside this, okay, then that's a hit. If it lands outside, it's a miss. How do I tell if my XY position that I land at is inside or outside the circle? Well, the circle is a unit circle. That means that if the distance from the center of the circle is 1 or less, it's inside the circle. Make sense? In other words, if the circle, because it's a radius of 1, so as long as we're inside the circle, it's going to be, our distance from the center is going to be less than 1. Make sense to everybody? So and this is something that unfortunately I had to learn plenty of. The way I know my distance, the distance from the center is equal to the square root of x squared plus y squared. Yep, x squared plus y squared. Square root of x squared plus y squared. Okay, so I've had to learn this plenty of times. So we square those values, and if it's more than 1, then we're outside the circle. So we're also going to need to import one more thing, which is math. Import math. And we're going to do this without the turtle being seen first, and then we're going to add the turtle to be seen. Okay. So def throw. We're going to throw and we'll take in Bob as the argument because we're going to be throwing Bob. But we'll do that. We'll do the actual moving him later. Okay. No, actually, why not? We can do it both at the same time, right? We're going to move Bob. We need to generate a random number. So our x is going to be equal to it's going to be equal to random Python. Oh, still plenty of time, Andrew. Got plenty of time. Okay. We need a number between 0 and 1. Like a function, sorry, a float between 0 and 1. I bet you it's called rand float or random.float or something. No, we've got one over here. It's never going to be 1, so uniform. Floating point number, such that it's a is in between the two. Excuse me, 1 second. Sorry. Oof, that's going to be terrible on the recording. Thank you. Okay, random.uniform 0. Oh yeah, it's going to be a random. So this can be, right. It's going to be somewhere between -1 and 1, right? Because that x coordinate could be from -1 to 1, right? Not 0 to 1, -1 to 1. And the y coordinate can be random.uniform from -1 to 1. It's going to be some floating point number in between those two numbers. Make sense? So Bob dot go to x comma y, and let's go ahead and just simply do a basic for loop over here. For in range, we're going to do this again. We'll do it as trials again. Trials is equal to, and I'm just starting out at 10 rather than 10,000 because we're doing this turtle stuff. Bob dot, and we're just going to simply call throw. We're not doing anything else. We're just testing the throw function. Why? Because, okay, yeah, sorry, forgot to tell him to throw Bob. Okay, Bob. Run, and we see that, yeah, let's go ahead and hit it again. Whoops. Let's go ahead and hit it again. Bob, you're moving very fast. In fact, so we can speed this up a bit. Oh, and sorry, no, trials, and then rather than doing 10, we do trials over here. So now Bob moves all over the place, right? So he's just going to a bunch of random positions. Let's go ahead and tell Bob to do pen up. Bob dot up. He doesn't need to go to 1, 1 anymore. And now he's just going all over the place. Very fast for a turtle, to be honest. Okay. So now we need to tell whether or not it's a hit or a miss, right? So so we're going to tell them to go that way. Actually, let's go ahead and calculate just this instead of doing it in an if statement. We're just going to do it as D. D is equal to math dot square root. We're just basically implementing the formula here. X squared, which is, and then times y squared. That's our formula for telling the distance. If we had 3 dimensions, it's basically the same thing. Okay, and now what we can do is we can say if D is less than or equal to 1, return true because that's a hit. Else return false. And now what we can do is that we can say hits. So instead of wins, we're doing hits. Hits is equal to 0. Trials is equal to 100. Throw Bob. So if throw Bob, if that's true, hits plus equals 1. And then we can print out. We're not going to go for the number of. We're going to print out hits divided by trials. Okay, hits divided by trials 1.0. Okay, that's probably not right. Let's see. Let's go ahead and squelch Bob for a second. Keep him from talking. 1.0. What did I do wrong here?
Is the distance supposed to be plus?
Yes, it's supposed to be plus. Got 2.75. There we go. 0.75. That's what we were looking for. 82. I know that doesn't sound that impressive, but remember, this is supposed to approximate pi over 4. So we're going to print out this number, and then we're going to print out this number times 4, which should get close to pi, which it won't. 3.2. I mean, I guess that's close-ish. But if we do this, again, 1,000 times, 10,000 times, we start getting closer and closer to pi, right? The approximation starts getting closer. However, this does not make you go, ooh, ah. We could have done all this without throwing Bob places. So let's go ahead and do egregious harm to our turtle, okay? So what we're going to do here is that we are going to tell Bob to go to XY no matter what. He's going to move no matter what. And then what we're going to do here is we are going to say, hey, if it's a hit, we're going to say Bob.color is red. We're going to change his color. And then Bob is going to stamp. And then Bob is going to do very similar on a miss. Only Bob is going to change his color to blue on a miss. Make sense? And now we get to have, and now, don't worry, I'll share this with you. But now we get to have fun. Well, it's going a bit slow, but we do have a comment up there that's supposed to help us. Which is, we are going to, at the beginning, do this. We're going to say Bob.tracer 1225. What in the world does tracer do? Control, always look up unknown functions. Tracer is an animation control. And it says only the nth screen update is performed, and then delay for upcoming drawings, so if you need delay between them. So this is saying only do every So instead of drawing every move the turtle makes, we're only going to draw, say, we're only going to draw whoa. Where'd my, oh, there it is. We're only going to draw, let's see, every 12th update. So now if I go ahead and run this, it went pretty quickly. If I go up to like 40, let's see what happens. Yeah, it goes very quickly. Okay, this doesn't look that impressive, but now that we're going fast, let's go ahead and do 1,000 trials rather than 100. And there, we're getting our circle. Because everything inside the circle is a hit. So we can visually now see our turtle being, turtle performing the hits as he gets the wall. So there we go. Hits times 4. And now 10,000. And we'll start getting really good results. As you can see here, it really kind of does even out. I like this one. Actually, this is this exact same, this test to see whether a dart hit pi was actually what I used for my project when I was doing my master's, when I was doing distributed computation. Because it's a matter of, it's a very easily distributed process where basically you can have multiple identical boards and combine the result. That was loud. Multiple identical results and combine boards and combine the results. Let's see. I believe. All right. So, calendar time. This is currently week 9, I believe. Right? This is week 9 of the semester. Don't think we're going to be ready for an exam next week. So, next exam will be on April 4th and April 7th, respectively. Got it? What will be covered in that exam? Let's go ahead and take a quick look at that. I will send this out. I will send a revamped version of this out later in this. By next week. But let's go ahead and take a look at the kind of things I care about for this. Come on. Uploaded media. Do I have that? Exam practice 2. There we go. Exam 2 practice. A couple of questions over here that are good theory questions, okay? But a file reading question. One of the things that will be on the exam that will help you with these larger problems, because there will be less problems, they'll just be larger. One of the problems to make that less of a stressful is that I give you the exact rubric on the questions themselves. And those rubrics will act, because I've gotten better at doing this since I started, these rubrics will act as a guide for you. So here, a file reading question asking you to read a file and give me the hottest hot day and the coldest cold day. Extra practice there. Method writing. Given a word, if it has un in front of it, remove un. If it has no un in front of it, you add un to it. So untied becomes tied, unable becomes able, necessary becomes unnecessary. Find the difference between the biggest and smallest items in the list. Give me the first half of the list. Give me a string where that contains that returns true if it has cat in it, but the cat can be but the middle A in cat can be any character. So, right, we can do tomcat or leet speak cat. So just some basic kind of questions that aren't necessarily for loop, but basically are list kind of based questions. Given an integer, return the sum of digits from 0 to 9. There's a lot of ways to do that. Finally, there will be a Monte Carlo question. This one was basically what are the chances of you rolling 2 dice of the same face in Monopoly, and then the consequences of that in Monopoly. Given a string, write a function that returns the most common letter in the string. Use a dictionary to do this. I will review that. And then here's extra practice for Monte Carlo, right? So again, there's going to be one Monte Carlo question, one file reading question, and the rest are going to be the kind of like those method questions that are fairly straightforward. Not fairly straightforward. And there's going to be, and again, the practice exam is going to be longer than the actual exam, and the questions will be more difficult than the actual exam. Okay? I always try to make the practice exam harder. All right, with that, let's go ahead and hit stop. Your primary audio source is quiet or silent. I doubt it.